eco-friendly process and for a better optimized process. So basically, everyone we each of one knows about what is sustainability. So sustainability in the VAM process is increasingly important topic as the industries are adopting VAM not just for its design or the flexibility or the cost advantages, but also for its potential to support the environment, economic, and the social sustainability. So let's start with the presentation. So either we talk about the additive manufacturing or the additive fabrication or the additive techniques or the additive layer manufacturing, the free from fabrication or the rapid prototyping or the 3D printing. These all are the different names for the process with the similar principle of operation. The additive manufacturing is a computer controlled process that creates a three-dimensional object by depositing material, usually in the layer over the layer. So, a brief introduction about the VAM or the metal additive manufacturing process. It was first being used in 1981 by the Dr. Hideo. He was being named as the inventor of the process, but the first patent was being done by the Chuck Hull in 1986 on stereolithography. The next patent was for the selective laser sintering by the Carl Deckard, and so on. When we talk about the basic additive manufacturing techniques, the first thing that comes in the mind, the material. So all the material or the most of the material or the majority of the material are polymer based. So the material could be either ABS or a PLA or the nylon or the epoxy or the resins. Means the different processes that we are going through uses different types of material. But mainly all the material or the most of the material are the nylon based or the polymer based. But as we talk about the mechanical industries, as in mechanical engineer, all the high-end technology businesses, either we could take it the automobile sector or the aerospace sector, uses a large amount of metal. So it is not the right thing to use additive manufacturing only for the polymers, as these metals, the metal that will be used by the aerospace or the marine industry or the energy sector or the automotive industries, these metals are costly and must not be wasted in machining, must not be wasted by subtractive manufacturing. Hence, these industries were the early adopters of the metal additive manufacturing. What is the basically the metal additive manufacturing is the metal additive manufacturing use the metals to create a layer by layer object. The production of the consolidated part can be done with the reduced labor or the weight. Overall, more efficient part with the increased complexities can be made. That part is not supposed to be made with or very hard to made with the subtractive manufacturing. The consistency and repeatability are the advantage of the additive manufacturing processes. Either we talk about the metal or we talk about the polymer. The better performance for the fewer parts. We can develop a part, we can develop an object, or we can develop a product with a fewer numbers of part. A very high degree of precision can be get from the additive manufacturing, and also the low buy to fly ratio. So basically, for my presentation or for the sake of knowledge, I have classified the metal additive manufacturing process in two types: the beam based process and the arc based process. In the beam based process, the heat sources are the laser or the electron beam, while in the arc based, the arc is the main source of heat. The arc either from the GMAW process or the GTAW process or the plasma process. The feed stroke used in the beam based are the wire as well as the powder, while the arc based process use only wire as their feedback. So, a brief introduction for the laser based additive manufacturing or the electron beam based additive manufacturing. The slide shows the electron beam additive manufacturing. It is a type of additive manufacturing for the metal parts. The raw material, that could either be the metal powder or the wire, is placed under a vacuum or fused together from the heat that is being generated by the electron beam. This technique is distinct from the selective laser sintering, as the raw material fuses have completely melted. It has the advantage is that it has a various advantage of the good layer thickness, the lower distortion because of the concentrated energy beam. Best near to net shape can be availed among all the other additive manufacturing processes, and above all, the workpiece properties like reflection or absorption does not create any problem But there is some disadvantage also, as the electron beam additive manufacturing process needs a vacuum chamber, as a vacuum is needed to for the traveling of the electron. So the vacuum chamber cost is quite high and the product size could be limited because of the size of the vacuum chamber. As we talked about the electron beam additive manufacturing process, so the next process is the laser beam based metal additive manufacturing process. So this shows the laser based process which create suitably shaped solid parts from a powder or the liquid. It has a lower setup cost as compared to the electron beam additive manufacturing process, and no size limit, because there is no vacuum chamber is required, so no size limit is there. The work area can be as big as the movement of the arm of the robot or the movement of the laser beam. But it also has some disadvantage, like it has a low deposition rate, or by using the laser we are creating some harmful radiation that can be harmful for the worker as well as for the environment. And second, it provide us a high heat localized zone that could create some problem either in the metallurgical part or either in the mechanical part, in the form of residual stresses and all. So this slide shows the basic operation of GMAW process, how it occurs. Like when the electric arc is established and maintained between a base material and a continuously fed wire electrode, the molten weld pool is shielded from the atmospheric condition by an envelope that has been created with the help of the various shielding gases that is being flowed continuously around the wire filler metal feeding in the weld pool and the weld pool itself also. So the heat of the electrical arc that serves to locally melt the base material as well as to melt the wire filler, the metal that is being fed into the weld. So there are four main variations of the GMAW process that could be available for us, that affects both the penetration profile of the base material as well as the weld bead profile above the base material for the given weld. The WAM technologies processes that are being shown uses these the welding current, the welding voltage, the contact tip to the work distance as well as the travel speed are there. So coming back to our topic of sustainability in wire arc additive manufacturing. So in this slide, we are going to study the sustainability and how it affects or how it create any difference in the wire arc additive manufacturing process. So as we know that the manufacturing has been always been judged on the basis of either cost or either the quality or the productivity. But nowadays or in the present time or in the present scenario, the fourth dimension, the sustainability, has become the equally important, as the industries worldwide are under the pressure to reduce the carbon emission that is being generated in the process that they are using, or to conserve the resources, or to adopt the greener processes. So WAM, which is an additive manufacturing process that is based upon the arc welding, is attracting attention not because it is able to make large or the complex parts or the large or the complex objects, but also because also because it has the potential to make the manufacturing more sustainable. Like if we explore that how WAM helps in the material saving or the energy efficiency or the repair or the recycling of any damaged product, or the how can we reduce the environmental impact. We will also look for its challenges and the innovation in this lecture, so that we can make it more sustainable. And by the end of the session, I hope you will all be able to connect the WAM as not just as a manufacturing technology, but as a contributor to a global push for the sustainability. So before we dive into the WAM, what is sustainability is, let us understand that what is sustainability is. So the most widely accepted definition for the sustainability could be, the sustainability means meeting the needs of the present without compromising the ability of future generation to meet their own need. So it rests on the three pillars, and the three pillars are mainly the environmental sustainability, the economic sustainability, and the social sustainability. For the environmental sustainability, the resources that we are obtaining from the environment, or the output or the outcome, the adverse output or the outcome that we are providing to the environment can be considered like reducing the material waste, the lowering emissions, the saving energy, or conserving the natural resources. Apart from the environment, economic sustainability is also a part of the sustainability, as here we need to ensure that the process remain cost effective as well as the competitive while being eco friendly. We cannot compromise with the uh, harmful or the damageable things if we are having some profit in the monetary benefit, or we are having some profit in the monetary form. And the third pillar of the sustainability is the social sustainability, through which we can create safe or the meaningful jobs or the opportunities for the people, so that the society can get benefited with the technology. We need to ensure that the social sustainability should be there. The social sustainability should be will be there when the economic sustainability will be there. But because of these two, we should not hamper or we should not compromise with the environmental sustainability. So this is the of the basic introduction of the sustainability. As we are applying this concept to the manufacturing, that means we must design and use the process that consume less raw material, generate less waste, consume less energy, and reduce harmful impacts, all while staying economically viable as well as the social beneficial. So our next slide shows the additive manufacturing and the sustainability, how the additive manufacturing can be sustainable, or what steps we can take to make our additive manufacturing process sustainable. So like the unlike the unconventional manufacturing that we cut material away from the bulk block or the large block, that as we are talking about the subtractive manufacturing, so the additive manufacturing builds parts layer by layer. The approach of building parts or building product layer by layer immediately improves the sustainability, because it uses only the material that is been needed, resulting in the less use of material. That means that results in the less waste, as well as it enables the lightweight or the optimized designs which are not possible with the conventional machining. For example, if we take an example of any aerospace industry, uh, the lighter components means the less fuel will be consumed and the lower emission will be there. Apart from the lightweight or the optimized design, the another key advantage is the repair and the remanufacturing. While additive manufacturing, instead of discarding damaged part, we can add some material back on where it is needed, extended the life of the component, as well as it reduced the need of new raw material extraction from our mother earth. Among the many other additive manufacturing techniques, wire arc additive manufacturing process is one of the most promising for the sustainability, because it can produce large near to net shape metal parts more effectively and at the lower cost. So when we proceed further in our presentation, so mm, how it connects, or how the WAM connects to the sustainability. So there are five main dimensions that we need to analyze when we are adding or when we are analyzing the sustainability in the WAM. The first one is the material efficiency. The WAM uses the wire feedstock with almost no waste. Unlike machining, most of the material ends up in the chip. So WAM deposit only what is required and where it is required. The second dimension could be the energy efficiency. The WAM consumes less energy than the laser or the electron beam additive manufacturing process, since it does not require the vacuum chamber or the extremely high power lasers. The life cycle impact is also it's also a dimension for the sustainability in the WAM, as one of the biggest sustainable advantage is that the WAM can be used for the repair and the remanufacturing. Hence, instead of throwing away a worn or a damaged part, we can rebuild the damaged area and extend its life cycle. So a lot of impact can be good impact can be generated on the environment, because we are reducing the waste in the environment, as well as we are reducing the extraction of newer raw material from the earth. The environmental benefits is also there, like it reduces the CO2 emission, the less transportation, because the VAM can be done near the point of use where we are going to use the object, where we are going to use the product. The VAM can be done at the place, as well as the less waste contributes to a smaller carbon footprint. As we are generating a less waste, less amount of waste, that means a smaller carbon footprint will be there, a smaller wastage, or the smaller amount of waste will be created for the environment. Also, the VAM reduces the cost by saving the material. It also reduces the lead time, as well as it also lowers the dependency of the centralized manufacturing. Hence, it provides us an economic impact. It also supports the local production and the job creation also, resulting in the more economic impact for a person working for any firm or the any industry. So, as in the previous slide that we have seen, most of the qualities or most of the dimensions were related to the material that we are using. Hence, the material efficiency in the VAM could either be could be the big advantage of the VAM when we talk about the efficiency, apart from the energy efficiency also. So, in the manner like, if we talk about the energy efficiency, so many additive manufacturing processes, sorry, so we are talking about the material efficiency, not the energy efficiency. So one of the strongest sustainability features of the VAM is the material efficiency. In the traditional subtractive manufacturing system that we are talking about, the machining processes, we start with a big block of material and then cut away the most of it to get the final shape. For the aerospace part, it is often meant using only 10 to 20% of the block, and the rest became the scrap. The ratio is called the buy to fly ratio. For example, if we buying 100 kg of titanium for any aerospace application, and the final aircraft part weight only 10 kg, that means our buy to fly ratio is 10 is to 1. That means 90% of the expensive titanium or the expensive material becomes waste. So the VAM changes it completely, since it uses the wire feedstock and the deposit material layer by layer. The material utilization is close to the 90 to 100%. That means almost everything we fed into the process goes into the part. This not only saves the raw material but also avoids the environmental impact of mining, the extraction of the new raw material, the processing, the post processing techniques that we need to perform before the part goes into the market, and the recycling of the large amount of scrap metal, because the recycling of the scrap metal also uses a large amount of energy, and that directly or indirectly affects the environment, that directly or indirectly affects the economic status of the country, and it also affects the it also affects us into the social form. So in short, if we conclude this slide, so the VAM significantly reduce the waste. It improves the material efficiency and makes the industry more sustainable, especially where the material like the titanium or the inconel or any other costly material are being used. So apart from the material efficiency, the another thing that we can discuss, or the thing that we need to discuss, is the energy efficiency in the VAM. The many additive manufacturing processes, like the laser powder based fusion or the electron beam based additive manufacturing, requires a very high energy beams. So they also need special environment like the vacuum chambers or the controlled atmosphere. And also these setups consume a lot of electricity, not only for the melting but also for maintaining the operating conditions. The operating conditions that we talk about, like the vacuum chamber or the controlled environment. So the VAM, in contrast, uses a conventional arc welding power source that does not require much energy as compared to the other processes. The energy requirement is significantly low, There is no need for the large vacuum chamber or the expensive laser optics or the different types of controlled environment. For example, if we compare the production of same large titanium part by machining versus the VAM, so machining not only waste material but also consume high energy for cutting and cooling, while the VAM deposit only the required material and consume less power overall, making it the far more energy efficient system. So in terms of sustainability, the VAM reduces the carbon footprint per part by consuming the less energy and enabling a near to net shape in manufacturing. So when we are talking about the energy efficiency and the recycling or the remanufacturing of the product, so the life cycle impact of the VAM should also be considered, as this is another critical sustainability dimension which impacts on the product life cycle. So in the conventional industries, I am again and again talking about the conventional industries because most of the industries in India is still using the conventional technology to prepare the part or to manufacture any component. So in the conventional industries, when the part is been damaged or the worn out, it is usually scrapped or replaced with the new one. That means more raw material has to be have to be mined, the more raw material have to be processed, the transportation of the material will be there, the manufacturing or the forming process of the casting of the material will be there, all of which increase the environmental impact. So when we talk about the VAM as compared to the other manufacturing or the conventional or the subtractive manufacturing processes, the VAM provides a better alternative. It can be used for the repair and the remanufacturing instead of discarding a damaged part. The VAM allow us to add a new material only where it is needed. For example, if we need to repair a turbine blade tip or a worn out propeller edge or a damaged mold, like we are that the diagram is being shown as a worn out propeller that can be repaired by the VAM process. So there are mainly three sustainable benefits. The first is the extended component life cycle. That means the repaired part can be used again, delaying the replacement. It saves the raw material as no need to extract and the process a complete new block of material is there, and also it reduces the environmental footprint, like lower emission will be there, the lower waste and the less energy consumed throughout the life cycle. So it not only builds a new part but it also gives existing part a second life, which is an essential part of the circular economy also. So what sort of environmental benefit, when we talking about the material efficiency, when we are talking about the energy efficiency, when we're talking about the repair and remanufacturing so that the new raw material can be saved, so what type of or environmental benefits a VAM can provide us? First, because as a VAM uses a near to net shape manufacturing process, a VAM is a near to net shape manufacturing process with a very little waste and overall carbon footprint per part is reduced. So, if we waste less material, it also means that the less energy is spent on the mining, refining, or the recycling. Secondly, the VAM enables the localized production. Imagine you are on a offshore oil ring or in a remote defense base, somewhere in Kargil or somewhere in Bikaner, where it is very difficult to transport large spare parts. That as the parts are very expensive or the transportation is very expensive, and also create a huge carbon footprint. The transportation creates a huge carbon footprint by using the diesel or the petrol in the vehicle. So with VAM, you can carry the wire feed stock and a portable VAM system and produce a part on site. This reduces the logistic and the emission from the transportation. Also, the VAM generates the minimum waste as compared to the machining. With the traditional subtractive manufacturing, a large percentage of material ends as a chip, which needs the further recycling. So VAM almost eliminates the problem. I'm not saying that the VAM is 100% accurate, but the need of the post processing is only very little. So now let's look at the economic impact of the VAM, which is closely linked to the sustainability. First, the VAM offered low cost production because of its high material utilization. Almost all the wire fed into the process become the part of the component. That is a huge cost saving as compared to the machining, where the expensive material like titanium or the inconel can have up to 80 to 90% of the wastage. Second, the VAM enables the shorter lead time. The traditional manufacturing of a large metal parts often require casting or the forging or the extensive machining, all the three or the different processes together. So the processes that can take months. So the VAM builds the part layer by layer directly from a CAD model, cutting down into the production time or the dwell time. Also, the VAM supports the localized production. That means the part can be built close to whether they are needed. That reduce the dependency of the global supply chain, avoids the long shipping delays, and even create new job opportunities in the local workshop and the repair system. So, economically speaking, the VAM is not only cheaper but also a faster and the more what we can say that the more resilient, all while supporting the sustainable development. So when we compare the VAM with the conventional manufacturing, so that we can clearly see the sustainability advantage. In the subtractive manufacturing, like the CNC machining, we start with a solid block and remove the large amount of material to achieve the final part. That leads to a high level of scrap, especially for the expensive material like titanium or the inconel or the different or the any other costly material that will be very painful. The high energy consumption for the machining and the cooling, also the long lead times because the part must go through the forging or the casting and the machining steps. In contrast, the additive manufacturing, or when we talk about the VAM in particular, it builds the part layer by layer using only the material required. So it provides us a better buy to fly ratio, as close to 1 is to 1 in many cases when compared with the 10 is to 1 in the aerospace machining, like we discussed in the previous slides. The overall energy consumption is reduced since the machining and the remelting is minimized. The significant cost saving are there as the raw material waste and the production steps are reduced. So the WOM demonstrate a clear sustainable benefits when compared with the traditional manufacturing in the terms of the material, energy, or the cost. So in the concept of the circular economy and the WAM, in traditional linear economy, the model is simple. The linear economy means the conventional economy that we were using in the past days, that we are having a abundance of resources. We were allowed to waste the resources as the resources are there, and we are very lucky at that time that we do not have to worry about the various resources or the various things that are going to be extinct soon. Some of the materials or some of the resources our grand generation, the third or fourth generation, can never avail. We are under such situation. So when we talk about the uh, traditional linear economy, the model was very simple: take, make, and dispose. All, that's all. So if we extract raw material, make a product, and use it and throw it away, so approach is not sustainable because it consumes new resources or it generates the waste. On But in the circular economy, it is different. It focus on reduce, reuse, recycle, and remanufacture. Instead of discarding the products, we try to extend their life, reuse the material, recycle the material whenever possible. So the VAM, the wire arc additive manufacturing process fits perfectly into the model because it supports reuse and remanufacturing instead of scrapping or damaged. We are taking in an example of a turbine blade. So Instead of scrapping a damaged turbine blade or a propeller, the VAM can repair it by adding material exactly where needed. It extends the product life cycle also by repairing the part, as the repaired part can serve for many more years, reducing the need of new product or the newer raw material. It also promotes the resource efficiency. Nearly 100% wire utilized means minimum wastage and the fewer raw material need to be extracted from the earth. The VAM is not only an advanced manufacturing process, but it also a key enabler for the circular economy in the metal industries. So, up to now, we have focused on sustainable advantage or the sustainability advantage in the VAM, but it is also important to look at the challenges that still need to be solved, like high heat input. Since the VAM is based on the arc welding and the process generates a lot of heat, this can lead to the residual stresses or the distortion or the defect in the build part. That means some extra machining or the heat treatment may be required, which consumes more energy or the which consumes more energy and reduces the sustainability. The another challenge could be the surface finish. The VAM parts typically have the rough surface and the large layer height. That means the post processing, like the machining, the grinding, or the polishing, is necessary to achieve the required finish and the tolerance. Again, this adds some cost and energy consumption into the process. The energy efficiency depends upon the process control. If the process is not optimized, for example, the wrong deposition pattern or too many reruns are there, the energy efficiency can lost. The proper monitoring and the control are very essential. The last one is the limited automation and the monitoring. Unless the laser bed additive manufacturing, VAM still lacks the wide spread adoption of the advanced sensors, the AI, or the closed loop control system. As without these, the sustainable potential cannot be fully used or can be fully realized. So, to overcome the challenges that we have discussed in the previous slides, some of the researchers or some of the industries are working on the advancements that make the VAM more sustainable. Hence, the process monitoring or the closed loop control. So, with the different types of sensors, with the different types of cameras, the thermal imaging cameras or the high speed cameras or the AI based control, the VAM can adjust parameters into the real time, in the real time, to maintain stable deposition, to reduce the defects, and to save both material and the energy. The hybrid VAM and machining systems can also be used. Instead of doing all the machining after the part is fully built, some machine tools or some machine can combine with the VAM in the same setup. This way, the part is machined immediately after the deposition, improving the accuracy as well as reducing the extra post processing time. The wire preheating or the advanced torch design can be used as a new torch design, including the water cooled torches or the preheat wire, improves the efficiency by reducing the heat input problems, stabilizing the arc, enhancing the deposition quality. Or this directly reduces the energy consumption and improves the material properties. Also, the use of renewable energy sources. Some of the industries are experimenting these renewable energy sources are not there in the market yet, and if they are in the market but they are not widely spread or widely being used into the industries. But some industries are experimenting with the powering the VAM system using the solar or the wind energy, further trying to further reduce the carbon footprint into the production. So these advancements shows how the VAM is evolving, not only to be technically better but also to become a truly green and sustainable manufacturing solutions. So we are taking an example of aerospace. So aerospace companies are under huge pressure to meet the sustainability and the net zero emission goals, and the VAM plays a key role in helping them, like the lighter aircraft. The VAM enables near to net shape and optimized design, which means the less material is used and overall aircraft weight is reduced. A lighter plane can consume less fuel, producing fewer CO2 emission over its lifetime. Also, reducing the titanium waste, as the titanium material is being used in a uh, very large quantity in the aerospace domain. So, as the machining of the titanium part can waste up to 80 to 90% of the block material, like that we have initially discussed. So VAM uses almost 100% of the wire feedstock, saving both the cost as well as the energy in the raw material production. Also, the VAM allows the aerospace company to print parts when and where they are needed. This shortens the supply chains, reduces the transport related emissions, and cut down the storage cost. Also, by as we are talking about reducing the material waste, or we are talking about the improving the energy efficiency and lowering emissions, the VAM aligns with the net zero roadmap of the aerospace giants like the Airbus, Boeing, or the Rolls Royce. So VAM is not just a manufacturing techniques; it becomes a strategic tool for the various aerospace industries to achieve their long-term sustainability targets. Like in this slide, this is a landing gear. This landing gear is being fabricated or being manufactured with the VAM process. So, if we talk about the marine or the offshore industries, as like the aerospace industries that we discussed in the previous slide, uh, the components are large, expensive, or often damaged in service. So instead of replacing the whole part, the VAM can repair the damaged area, saving the raw material and the energy. Also, the large size component manufacturing is, can be done through the VAM. The traditional casting or the forging for such parts are expensive, time consuming, and the wasteful, as a lot of amount of machining needs to be done. So VAM offer a more material efficient and the cost efficient alternative. Also, it reduces the downtime or the material waste. If a suppose if a ship has a damaged propeller, so waiting for the replacement, we can repair the propeller with the help of VAM. On-site production can help in the oil rigs, the marine repair yards, or the various defense bases, where we could use a portable VAM system to build or to repair the required part. And also it is also beneficial, as it reduces the as it reduces the emission. So after the aerospace industries or the oil or the marine industries, we can also use the VAM process into the automotive industries or the tooling industries. As the traditional die involves a heavy machinery or a long lead time, the VAM can reduce these things. The repairing that we have discussing again and again, that we can do through VAM, the rebuilding or the remanufacturing or extending the tool life. The lightweight structural components for the aerospace or the automotive can be built by VAM, which will decrease the consumption of the fuel, as well as when the fuel consumption is decreased or reduced, the emission will also going to be reduced. VAM help by enabling the optimized geometries with the less material waste in this domain, in this part. Also, the development cycle for the particular part or the for the particular object can be reduced, as the VAM can quickly produce the prototype for the new design. So in the automotive or the tooling domain, by reducing the waste or by extending the tool life or by lowering the cost or by enabling the faster innovation, the VAM contributes to a large scale. Also, the repairing of the turbine blades could be there in the renewable energy sector. The on-site manufacturing could be there on the in the renewable energy sector. The lead time reduction for the critical component, those are really needed in a very less amount of time, can also be done through the VAM, or can easily be achieved through VAM. and also by saving the raw material, or by cutting emission, or enabling the fast repair, the VAM directly support the shift toward the greener or the renewable energy system. Also, for the sustainability through VAM, the greenhouse gases reduction into the environment is also a very significant point or significant topic to discuss. The wastage through the traditional manufacturing can be reduced in a very large amount. So we can discuss only when we can deposit only when the needed, reduce transportation through on-site production, energy efficiency with the optimized deposition, as compared to the large size forging or the casting processes where the large amount of machining is required after the process. The VAM system can increase the energy efficiency with the AI and the automation as well. So it also supports the circular economy and the net zero goals by enabling the repair, reuse, or recycling of the metal parts. The VAM helps the industries to reduce their total carbon footprints and align with the net zero emission targets set by the government or the global climate agreement. So when we talk about the circular economy, which is all about keeping the resources in use for a longer duration of time, or for as long as possible. So through reduced waste, the circular economy can be achieved as the minimum scrap, or keeping the material in circulation instead of sending them into the wastage. The repair and remanufacturing of the part that is being discussed in the previous slides many times will also help, or will also support the circular economy. Recycling of the unused feedstock that are not like the metal wires or the powder not consumed in the build can often be reused in the next job. We can collect the powder, we can filter the powder, we can reprocess the powder, and can use the powder again and again if you are using any powder based metal additive management system. And of course, by enabling the repairs, we are and extending the component life cycle. The longer life cycle means the less frequent replacement, conserving resources and reducing emissions. So when we are here done with the sustainability in the VAM. So if we thought about the different part of the coin that the VAM has, it is called smart manufacturing. Through smart manufacturing, we can assure the precision, we can assure the accuracy, we can assure the repeatability. So for these types of things, or for the energy efficiency also, some advanced mode of manufacturing is required. So what is smart manufacturing? So everyone might be knowing the smart manufacturing, but just a brief explanation, or just a brief discussion on the smart manufacturing. The smart manufacturing is a modern approach to production under the industrial 4.0 framework. It is not just about the automating the machines, it's about connecting them, making them intelligent, and then allowing them to adapt into the real time. If we talk into the similar terms, the smart manufacturing integrates the technologies like the artificial intelligence, or the IoT, or the robotics, or the data analytics into the manufacturing process. The main aim is to create a system that not only uh, automated, but also the self optimizing. That means the process that learns from the data, respond instantly to the changes, and make decision without the wasting of human intervention. So instead of trial and error manufacturing, we can have intelligent or a data driven production that ensures the high efficiency, the good quality, as well as the high consistency. So why the smart manufacturing in the VAM is required? VAM is a powerful technique, but it has some challenges. For example, the controlling of heat is very difficult, and if you don't manage it properly, it's lead to the residual stresses, or the distortion, or the cracks, or many other defects could be arises. So the surface finish or the dimensional accuracy are also a big concern for the researcher or the industries that are using VAM. So this is where the smart manufacturing become very critical, as by integrating the sensors or the IoT or the AI, we can make WAM the more reliable and the repeatable process. Smart system allow us to monitor the parameters in the real time and make adjustment instantaneously, rather than relying on the post process corrections. The another key point is that the WAM has shown a great result in the research labs, but scaling it up for the industry requires more stability and the consistency. The smart manufacturing bridges this gap and makes the WAM suitable for the aerospace, marine, and energy application where the quality cannot be compromised. So this is a basic layout of the smart manufacturing system that can be used into the WAM, where the designing or the processing of the WAM as well as the sustainability dimension or the sustainability points can be used and uh, can be monitored, or we can say that it can be analyzed through the AI model. So after the so the what could be the role of smart manufacturing in the WAM? So after understanding the challenges, the first rule is a real-time data acquisition, which help with the help of sensors like the thermal cameras or the current or the voltage sensors or the laser profilometers. We can continuously monitor the process. This allow us to know exactly what is happening during the deposition. Second is a closed loop feedback control. Instead of waiting until the part is finished, the system can make the adjustment instantaneously, like changing the wire feed speed or the torch travel, so that the bead shape or the quality remain consistent throughout. The artificial intelligence can also help in predictive defect detection. By analyzing the past process data, the artificial intelligence can forecast when porosity or where the porosity or the cracks or the distortion can occur, and can alter and adjust before they actually happens. Also, the robotics can be used for automation, as to make the WAM scalable. With the robotic arm handling the torch and the multi-scale motion, the complex geometry can be produced reliably with the with the very less dependency on of the manual intervention. So as we discussed in the previous slide, the different sensors can be used. So these sensors could be uh, the most important elements because they act as the eyes and the ear of the system. For example, for example, the thermal cameras can be used to measure the interpass temperature. This ensures that the next layer is deposited under the right thermal conditions, avoiding the excess heat accumulation that could result in the poor bonding as or in the delamination error. The acoustic emission sensors can be used to detect the abnormal sound in the arc or the material during the deposition. These sounds often indicates the cracking or the different other defects, which can be addressed into the real time. The laser profilometer can be used to measure the bead geometry, such as the width, height, the reinforcement, the dilution, or the penetration immediately after the deposition, which will help in maintaining the uniform uh, layers throughout the process. And also, the voltage or the current sensors can be used to monitor the arc stability. Stable arc is very critical, as a stable arc is very critical for the achieving a consistent or metal deposition and avoiding the defects like the lack of fusion or the reduction in the porosity. So altogether, these sensors generate the continuous stream of data that allows the WAM to be monitored, controlled, and can be improved in a real time. IoT is also a very what can we say, key player in smart manufacturing. If we're talking about the WAM, it is as it is as when we talk about the sensor or the data, it is not about the connectivity, or this is where the Internet of Things can play a role. The first, the IoT enables the machine connectivity or the communication. The WAM machines, the robotic arms, or the sensors can talk to each other and exchange data seamlessly with the help of IoT. Secondly, it also allows the remote monitoring or the diagnosis. The engineers don't always need to be near the machine. They can monitor the process parameters like the temperature, voltage, or the any other processes that could arise defects or some difference in the outcome of the process, even across the globe. Also, the IoT ensures the cloud storage of the build data. Every layer information can be uploaded and stored, creating a complex digital history of the component. This could be vital for the traceability, especially in the industries like the aerospace, where the certification requires the detailed recordings. And also, the IoT can support in the distributed warm cells, WAM cells. This means the factories in the different locations can be connected and can be synchronized, allowing the global manufacturing network to work together very efficiently. When we're talking about the sensor, when we're talking about the IoT, so artificial intelligence is also a powerful tool that can be used into the smart wire arc guided manufacturing system. Firstly, the machine learning algorithms can be used. The machine learning algorithms can analyze the past build data and learns the pattern that leads to the defect, such as the porosity or the crack. By recognizing these patterns, the AI can predict the defects before they actually happen into the process or into the running process into the real time. Secondly, the AI can tune the process parameter into the real time. For example, it can adjust the voltage or the wire feed speed or the torch travel speed automatically to maintain the stable deposition and the consistent bead morphology. Also the computer vision systems uses camera to inspect the surface quality of each layer. They can detect irregularities like the roughness or the incomplete fusion, immediately avoiding the build failure. Sorry. And also, the neural network can be trained to develop optimized build strategies. Instead of trial and error experimentation, AI can suggest the best combination of parameter for a specific material or the geometry or the application. When if we use the digital twin, it could be the another key element of the smart manufacturing applied into the WAM. A digital twin is essentially a virtual replica of the actual WAM process. It allows engineer to simulate the heat transfer during the deposition, so that it can predict how heat will accumulate and where the residual stresses might be formed. This is important because as too much heat can cause distortion or the cracking. The digital tints also helps in predicting the mechanical stress or the distortion or even the microstructural evolution, or if any correction in the microstructural evolution is required, we can find or predict through the digital twin. As uh, we can know in advance what kind of grain structure or the mechanical properties will be resulted from a certain process path. The digital twins is also very important in tool path planning, as instead of experimenting on the machine, we can optimize the path of a robotic torch virtually to minimize the defect as well as the distortion. The biggest benefit is that it approaches the reduced failed builds. Since we already know how the process will behave, we can save both the material both and the time by reducing the trial and error in the process. So the basically the digital twin act as a testing ground where the mistakes can be made virtually, not physically, making the wire arc ID manufacturing process the most cost effective as well as the most reliable process. Also, as we are using sensor and we are using sensors for the real time application, so the closed loop feedback system is very essential or is very much required So closed loop control is the most important aspect of the smart manufacturing. As in simple word, the system is being continuously monitored what is happening and automatically corrected into the real time. From with the help of the outcome that we are generating, we can easily alter the process statement or the process parameter that can be used in the process, and through which through those any defect can be arises can be eliminated. For example, if the bead height starts becoming too tall or too short, the system immediately adjusts the wire feed speed or the travel speed to bring it back to the desired level. Suppose if the arc voltage become unstable, the controller can fine tune it to ensure the stable energy input. Similarly, the torch movement can be corrected if the deposited path deviates from its original trajectory. Also, it has the biggest advantage that the consistency is maintained throughout the build. Instead of discovering the defects at the end of the process, the closed loop control system prevents them during the process. So the closed loop control system or the closed loop feedback system uh, transform the VAM from the semi-manual or the error-prone process into a highly controlled self-correcting system, just like the modern CNC machines achieve the precision by continuous feedback. Excuse me for a minute. Excuse me for a minute. I'll just take 10 to 15 minutes. Just a second.
So guys, we are having a 5 minutes break. Afterwards, we will start.
Uh, Thank you, participants, for your consideration. Is my slide visible? Okay. So after the closed loop control system, if we talk about the process automation with the robots, the robot the robotics can play a central role in making the VAM fully automatic and the industry scalable, as the robotic arm can be used to carry out the deposition process. They can precisely control the movement of the torch or the wire feed, ensuring the accuracy in each and every layer. Secondly, the advanced robot offer multiple axis control. That means the system can deposit metal not just in the straight line or the simple layer, but in complex or the free-form 3D geometries that are difficult for the conventional systems. Also, the automatic torch positioning ensures the torch is always at the correct angle and the correct distance from the part. This is especially important in VAM because small deviations can lead to the lack of fusions or the proper bead quality or and many other defects in the VAM. Also, by reducing the manual intervention, the human error are minimized. The process become more consistent. The process become more repeatable, which is very critical for a VAM generated part. The VAM generates a massive amount of data during each build. The parameters, like the parameters that we can take, the voltage, the current, the wire feed rate, the temperature distribution, or the outcome that we can take as a bead height or the cooling rate, can be continuously recorded. This data is not just stored, it can be analyzed to identify the trends. For example, by studying the variation in the arc current or the bead width over the time, we can spot the early signs of instability in the process. Through big data analytics, we can also discover the defect patterns. If certain combination of the parameters always lead to the porosity, the system can avoid these conditions automatically. The another advantage is the predictive maintenance. By monitoring the performance of the torch or the wire feeder or the cooling system over the build, the data analytics can warn us before a component fails. It reduces the downtime and can increase the machine availability to us. So, finally, the analyzing the historical data support the better quality control can be generated. It helps in setting the tighter process windows, and it can ensure that the VAM parts meet the strict industrial standards. The cloud computing or the cloud manufacturing could be the major enabler for the smart VAM process. It shifts the manufacturing resources and the capabilities into the cloud, making them accessible from anywhere. It allows to remote access the VAM resources. The engineers or the companies don't have to be physically near the machine. They can upload the design, they can monitor the build, or they can even control the process through the cloud build platform. Secondly, the digital designs can be shared globally. A part design in one country can be directly manufactured in the another using the same digital mode, which makes the VAM a truly distributed or the collaborative technology. Also, the virtual VAM labs or the simulations are possible. Instead of running costly physical experiments, or instead of conducting the costly physical experiments, the simulations can be run into the cloud to test the different parameters, predict outcomes, and only then be carried out into the actual build. Finally, the cloud platforms enables the on-demand manufacturing services. The companies that don't even own the VAM system can still use by accessing the manufacturing as well as the service providers through the cloud. The predictive quality control could be a game changer in VAM, as it helps to prevent the defect rather than just detect them afterward, or just detect them after the complete part or the complete object has been built. The process works by combining the sensors with the AI. The sensors continuously captures the information about the melt pool size, the bead geometry, the temperature distribution, or even the acoustic signals during the deposition. The AI algorithm can analyze this data in real time to predict whether a defect is about to occur or not. For example, let us suppose if the melt pool temperature start fluctuating beyond the safe range, the system can predict the porosity or the lake of fusion may develop. Similarly, by monitoring the bead geometry, we can warn against the layer distortion or the poor surface finish. This approach prevents the issues like the porosity or the cracks or the distortion before they actually appears. It reduces the wasted builds or it reduces the material wastage. It saves the material, and it can ensure higher consistency into the part. Most importantly, the predictive quality controls help in producing certification ready parts, especially for aerospace or the defense industries, where the reliability and traceability of the parts are very critical. So, as we have already discussed the sustainability, we are discussing the smart manufacturing. So, how can we achieve the sustainability through the smart manufacturing in the WAM? So, one of the major advantage of integrating the smart manufacturing with the WAM is to get the sustainability into the process. The first WAM itself already reduces the material waste as compared to the traditional manufacturing systems. The smart WAM make this even better by optimizing the tool path and the deposition strategies to minimize excessive material. Also, the energy consumption can be optimized through the smart monitoring. Instead of running machines at the fixed parameters, or the smart control adjust every input precisely to what needed, saving the electricity as well as the requirement. Also, the smart WAM enables the recycling of the unused wire supports and even scrap materials. This contributes to a more circular economy model in manufacturing. Also, the distributed manufacturing through WAM, where the parts are printed closer to where they are needed, the significantly reduction in the transportation related carbon emissions could be there. So, uh, industry some of the case studies, we are taking some industry product or the industry parts and an example. The aerospace, as the aerospace one of the biggest adopter of the smart WAM process, because the industry requires a lightweight, complex, and the high strength component that is very expensive to produce using the traditional methods. Smart wire arc manufacturing help by ensuring the defect free build with the use of AI, the closed loop monitoring, and the predictive quality control. The process become more reliable enough to meet the aerospace industry standards. The digital tool technology is especially valuable in aerospace because a part is printed. The Before the part is printed, the simulates the heat flow, distortion, and the mechanical properties, ensuring the final product meets the certification requirement. And well-known example is the production of the large titanium structural component, such as the wing spares or the bracket. Using the smart WAM, these parts are produced faster with the less waste and at a much lower cost compared to the machining them for the solid billets. This proves that the wire IIT manufacturing process is not just an experimental; it is already been used to manufacture the critical aerospace parts. In the marine or the offshore industries, the components are often large, heavy, and very expensive to manufacture or very expensive to replace. The WAM is highly suitable here because it can produce a large scale component such as the ship propeller, the ruders, and even structural elements directly from the wire feedstock. The smart WAM further improves this by enabling the real time monitoring and the defect prediction, which is especially important for the marine applications where the corrosion resistance and the mechanical strengths are vital. The another major advantage is in the reducing the lead time for critical spare parts. Instead of waiting the weeks or the months for the replacement to arrive, the smart WAM parts allows to be manufactured on site or near the place where it is going to be served, saving both the time as well as the cost. The example is the on-site repairing of the marine component. The WAM can rebuild the worn out or the damaged section of the part layer by layer, restoring it to the working condition without needing the full replacement. This makes the smart VAM very critical for the marine industry, improving the sustainability, reducing the downtime, as well as lowering the operational cost. In the energy sector, whether it is the oil or the gas or the power generation, the components often operates in the extreme condition or the high temperature, high pressure, and the in a very corrosive environment. So the smart VAM is very useful here for the manufacturing the turbine blades, the valves, the pressure valves, and the drilling tools also. These are the high value parts which where the quality and the reliability cannot be compromised. Through the real time monitoring and the predictive control, the smart wire arc manufacturing prevents micro cracks, the porosity, or the hidden defects that could cause the failure in the services. A practical example is the customized repairing of the turbine component instead of replacing an entire turbine blade. The damaged portion can be rebuilt layer by layer, restoring the part to the original condition. That saves enormous amount of cost and reduces the downtime, so that the machine can be brought to the work very soon. Some of the benefits of the smart manufacturing that makes it more attractive for the industries. It's high accuracy and the repeatability. By using the sensors or the closed loop control and the AI, even the layer is deposited continuously, reducing the dimensional errors. The dimensional errors. Also, the smart VAM enables the faster production of the large parts. Unlike the powder-based 3D printing, the VAM has a high deposition rates, as the smart automation makes the process even more efficient. It also leads to the reduced material wastage and the cost. Since the wire is used as a feedback and the deposition is optimized, the wastage is minimal as compared to the subtractive machining. Also, the smart wire arc additive manufacturing process provides enhanced quality. The real-time monitoring and the predictive control detects the problem even before they occur, ensuring the reliable parts suitable for the critical industries. Also, the smart VAM contributes to the sustainable manufacturing with the use of less energy, with the use of material more effectively and in the more efficient way, and even the recycling possibilities. It supports the eco-friendly production models. Also, the Industrial 4.0 can be integrated with the wire arc additive manufacturing, as the VAM is positioned as a core process in the smart factories. Instead of being standalone machine, it becomes a part of an interconnected digital ecosystem. Also, it integrates with the IoT, the AI, the digital twins, or the robotics. This means the process is monitored, simulated, optimized, and automated in the real time, reducing the human intervention as well as the improving the precision. The VAM under the Industry 4.0 enables the real-time data sharing across the supply chain. For example, the design changes made by the engineer can instantly be reflected in the production, and the quality data from the manufacturing can fed back to the to improve the design used. Also it this integration supports the mass customization and the distribution in the manufacturing. The VAM can produce customized large scale metal parts on demand at different global location based upon the digital shared model. Although the smart VAM process have a huge potential, there are still some major challenges in the implementation are there. The basic challenge of the high cost is always there. The initial cost of the installing the advanced sensors, the AI system, or the robotic platform is very high. This makes it very difficult for the small or the medium enterprises to adopt this smarter way of manufacturing. The integration complexity is significant. Combining the various sensors, the various data analytics, the cloud system, or the robotics required a strong technical knowledge or the strong technical expertise, and achieving the seamless communication between these systems is not an easy task to be done. Hence, a highly skilled engineer or highly skilled expert is required. Also, there is a shortage of the skilled workforce, as the we are talking about the highly skilled expert is required. So there is a shortage of the skilled workforce. The engineers, the operators need specialized training in both the WAM process, that is the mechanical side, and the smart technologies like the AI, IoT, and the digital twins, the computer domain side. The standardization and the certification remains a hurdle. The industries like the aerospace or the defense require the quality certifications. Since the smart WAM is still evolving, the global standard for the testing and approval are not fully established right now in this domain. So while the technology is very promising, these barriers must be overcome before the WAM can be widely adopted by the industrial scale on a large scale. So this was all about the sustainability in the WAM and the smart manufacturing integration in the WAM. So basically, we are going to discuss a research case study for some time. So if we are using WAM, if we are uh, doing the metal additive manufacturing, it should have the following primary function. The high reinforcement should be there, because if we have more reinforcement, that means less amount of beads will be required to produce a particular part. Low penetration will be there. Low penetration means more amount of metal will be above the substrate plate. The more amount of metal above the substrate plate result in the more reinforcement. More reinforcement result in the less amount of reruns of the machine. Though low dilution is required, as the substrate plate is not being used in our product, the substrate plate will be cutted out from the final object. So low dilution is required. Low width is required, as the size that matters in additive manufacturing. If the width is high, if the width will be on the higher side, the more machining or the more post processing will be required. The high metal deposition rates results in the less amounts of rerun of the machine. Hence, the higher metal deposition in the WAM acts as a positive results. And also to save the energy, to save the to save the money, as the environmental sustainability, as a economic sustainability, low power users should be there in the machine. So for this case study, we have taken a process that is using a preheated wire into the welding torch, and apart from the preheated wire, we are also using a powder feeder. Through the powder feeder, the powder is being fed directly into the center of the arc. The preheated wire, the preheated nozzle that has two functions. First function is to preheat the wire so that the melting temperature of the wire can be reached early. So the primary circuit needs to provide a less amount of current. Also, the fluid across the section of the fluid across the cross section of the nozzle is being circulated to reduce or to conduct the excess heat from the nozzle to the environment. As if the temperature of the nozzle, if the temperature of the nozzle tip is less, that means less amount of resistance will be there in the nozzle. Less amount of resistance will result in the less amount of current drawn from the primary circuit. Hence, the less amount of current is being drawn from the primary circuit, the less amount of current will go into the substrate plate. Also, we are going to use a condition monitoring bed below the substrate. In this condition monitoring bed, we can do both the things. Either we can heat up the substrate plate wherever required, or either we can cool down the substrate plate wherever the required. For the particular case study, for the particular case study, we are using the conditional bed as a water cooled bed, where the cooling of the bed is been done. As the because of this cooling, the conduction of the temperature will be fast. The more conduction of temperature means lesser amount of temperature accumulation into the generated part. Lesser amount of temperature in the generated parts leads to the low fluidity of the metal, and the low fluidity of the metal will results into the more reinforcement. So the first part that we are going to consider is the advanced fluid cooled welding torch for WAM. How to prepare the fluid cooled welding torch for this case study. So these are the steps used for the design and the development of the fluid cooled welding torch. Firstly, the selection of material. Secondly, the designing of the welding torch. After the designing of the welding torch, the design of the torch has been fed to the ANSYS for the thermal analysis of the contact tip. Once the thermal analysis has been done, once the torch has been approved, the fabrication of the welding torch and the assembly and installation of the welding torch onto the WAM machine. So the first thing is the selection of material for the welding torch. So the material selected was the copper tellurium. It has a good machinability and the high thermal and the electrical conductivity. For the selection of material criteria, for the selection of material, the criteria that are taken into account were the thermal conductivity, the electrical conductivity, the machinability, and the lightweight. For the thermal conductivity should be good. So to enhance the heat transfer rate from the contact tip, so that the temperature can be controlled as per our desire. The electrical conductivity should also be good to transfer the current from the welding wire with the least amount of resistance to improve the efficiency of the welding power source, as the least amount of resistance will provide us the facility of limited amount of current that can be drawn from the primary welding source. Also, the machinability, the ease of fabrication should be there, as the design of the torch is complex, and also the lightweightness of the torch, so that it does not create any hindrance in the movement of the robotic arm, or the movement or the accuracy of robotic arm should not get compromised. So, after a thorough research, the material selected was the copper tellurium. It consists of the 99.2% of the copper, 0.7% of the tellurium, and the remaining amount of phosphorus. The tellurium also adds a benefit of good machinability. The copper is also a lightweight material with a density of 8.96 gram per centimeter cube only. Hence, the lightweightness of the component is also there. So, for the geometric parameters, for the selection of the maximum dissipation, the number of revolution, the width of cut, the depth of cut, and the length of the contact tubes were taken. For each parameter, three levels were chosen, and the three levels for the number of revolutions were the 1086. The depth of cut was 4.5 mm, 3 mm, and the 1.5 mm. The width of cut was 5 mm, 4 mm, and the 3 mm. And then the length of contact tube that we have tried was the 5 inch, 4 inch, and the 3 inches. The experimental run was being designed, and as per the experimental run, we have developed the different types of nozzle for the torch. This is the solid model of the torch along with the bill of material. The top cap, the inside screw, the outside annular, the gas diffuser, the connecting screw, and the contact tip were fabricated using the copper tellurium, while the bakelite was used for the bushes and the stainless steel was used for the water inlet and outlet. This is the basic view of the nozzle. In the center, this is the wire. We have used the graphite so that the buckling of the wire can be controlled. After the graphite, the copper tellurium part is there. Between this is the outer annular. This outer annular has also been made with the copper tellurium. Between the nozzle and the outer annular, there is some gap. This gap is being used to circulate the water into the nozzle. The nozzle design has been used in the spiral form to enlarge the surface area, so that the maximum amount of conductivity of the heat can be done. The analysis in the ANSYS were conducted using the two cooling modes, the air and the water. For the air cooling analysis, the outer annular was removed and it was assumed that the V grooves were in a direct contact with the ambient air, allowing for the free convection. For the water cooled analysis, the outer annular was assembled onto the design with the assumption that the water was pumped through the jacket, resulting in the forced convection. In this case, the V grooves were in the direct contact with the water, which carried away the heat. The thermal conductivity of the copper tellurium was considered to be 360. So a thermal load of 500 degree was applied to the assumed heated wire. The thermal load, that means the temperature of the wire, was calculated based on the length of the dielectric gap and the electrode stick out. The dielectric gap, the gap between the two polarities that we have provided for the preheating of wire. So these are the analysis analyzed geometries. These geometries were analyzed on the basis of the convection through air, and these are the geometries that we analyzed using the water circulation with the outer annular and guarded the nozzle. So on the basis of the various levels that we have decided to prepare the torch, we have done the analysis. The final temperature and the final temperature that we are achieving through air and the final temperature that we are achieving through water were analyzed. The temperature was obviously the temperature was lesser when the water is being circulated for the conduction. So the torch with the lesser amount of temperature has been selected as our fluid cooled welding torch. The advantage of this torch is the design is compact and can be used in 3D printing process very easily, and can be used for any general or the intrinsic designs. As the preheating of wire is already been there, so it will reduce the peak temperature and the cooling rate of weld material, which will result in a finer grain structure. Hence, increment in the strength as well as the toughness of the developed part can be achieved easily. Lower melting of the base plate, as we know the process of MIG, the 66% of the current goes into the torch and 33% goes into the substrate plate. If we are reducing the current requirement from the primary welding source, that means the 33% current will also get reduced. Hence, the lower amount of current has been gone into the plates. That means the lower melting of the base material will be there, which will result in the lesser penetration and more reinforcement can be achieved in our process. It will provide higher weld metal deposition rate at same welding current input. It will result in the lower heat affected zone, hence less chance of failure of the weldment. It also reduces the cost of power consumed, as it reduces the resistance. This we are going to discuss in our further slides. Once we are done with the fluid cooled nozzle, we have prepared a cooling bed. So this is the basic design and the assembly of the cooling bed. Once we have prepared the cooling bed, we have done a transient analysis simulation on the cooling bed. It takes around 17 seconds to get the temperature from 1650 degree to 104 degree. So that means the heat conduction through this bed is good, and because of the high heat conduction, the fluidity of material can be controlled. So after the once what is cooling bed? A cooling bed is a cubical shaped environmental conditioning bed designed for the metal 3D printing. More specifically, it provides a stable structure for the 3D printing material and also facilitate in easy cooling of the base plate. The cooling bed comprise of the different channel placed horizontally and parallel to the heat bed head. These channels features the holes on the top surface so that the water can be sprinkled on the top plate during the 3D printing material. The interpass temperature can be maintained as consistent, which is a very crucial uh, requirement of a VAM process, and the time consumed while the extruded material reaches its temperature is considerably waste, or it is called as a dwell time. Thus, the cooling bed helps to conduct the temperature rapidly and uniformly, reducing the dwell time and minimizing the defects like the wrapping or the distortion. Additionally, the cooling plate swiftly conducts the heat away from the extruded material, decreasing in the fluidity. This results in the smaller valve bead, and the more reinforcement is there. So, as the cooling bed is a very bulky product, we have used mild steel, a basic structural material for the preparation of the cooling bed. So these are some of the advantages of the cooling bed that we have already discussed, like the reduced dwell time, the high reinforcement height, as the fluidity of the material will be low weld bead will be there, hence high reinforcement will be there. High productivity. It can operate in both continuous or the batch modes, and no moving part is there into the cooling bed. That means the minimum maintenance is required. Once the cooling bed is been formed, we have also modified the powder feeder that has been taken or that has been bought from the market. So in operation, the feed screw rotates at a constant speed in the powder feeder, delivering a consistent flow of the welding powder from the hopper to the metering mechanism. The metering mechanism regulates the flow of welding powder into the arc, ensuring a consistent flow rate. This directed flow uh, produces a high quality weld. The screw type powder feeder offers a several advantage over the different types of powder feeder that includes the improved accuracy as well as the consistency, or the reduced maintenance, and the increased efficiency. This is the basic structure, or this is the powder feeder that we have used. So the study investigated the influence of the advanced welding process parameter, and with the use of powder. This was the exterior portion of the powder. This was the screw that we used to feed the powder from the hopper to the nozzle, and this was the gear train that is used to move the screw. So basically, in the operation of the powder feeder, the feed screw rotates at the constant speed, delivering and consistent flow of the welding powder from the hooper to the metering mechanism. The screw type powder feeder provides the several advantages that we have already discussed, and it provides a consistent flow. Also, when we are using the powder, we have checked and we have experimented that the amount of powder and the amount of wire should be equal for the maximum, for the most efficient deposition, and for the defect free deposition. So we have tested the wire feed rate, the speed of wire that the wire is melting, as well as the current that is being fed to for a particular wire feed rate, and the deposition that we are getting. E- these these were these are the gears that we use. These were the gear train that we use for our powder feeder. These are the three different types of grooves that we use into the powder feeder: the square groove, the V-shaped grooves, and the modified V groove. In the below table, we have also shown the flow rate into the grams per minute, so that we can assure the consistent flow of the powder. As the failures are the required part of the experiment, it provides us a good insight of the experiment. So some of the failures that I have shown with the different types of screws are these, and in the final, in the last, we have achieved a good surface finish, a good weld bead with the help of the powder feeder. These are some of the process parameters that we used for our 3D printing, or the mathematical modeling. For the development of mathematical modeling, these are the well beads. These are the results. Through the results, we can assure that the well bead was lower than the normal process. The NP shows the normal process, and the AP shows our process, the advanced process. The well bead, the increment in the well bead was not very high. The reinforcement increment was very high. The penetration decrement was good, and the dilution was also also was on the decremented trend. Also, the interesting thing about this process is the economics of advanced process. What is the economic of the advanced process? In the context of the GMW process, the significance of the electric power consumption cost becomes pronounced when substantial welding is required for the specific task. The electric power consumption cost of the GMW is initially dependent on the factors such as the welding current, the welding voltage, the welding time, and the cost of powder per kilowatt hour. So the electric power cost could be the results of the current, voltage, the welding time, and the power cost. The second outlines the correlation between the second equation outlines the correlation between the personal cost, the consumable cost, the electric power cost, which are primary component that significantly affects the total welding cost. As a result, the welding engineer prioritize in reducing these expenses while maintaining the integrity of the weld. So experimental trials were done to compare the electric power uses between the GMAW and the AGMAW process. Both welding processes utilizes the input parameter for the primary welding power with a voltage of 24 volts and the current of 190 amperes. So, however, for the advanced gas metal arc welding process that we have used for the WAM process, three alternative parameter sets were applied. For the set 1, the auxiliary power source was set to 0, the voltage and current replicating the normal GMW method. In the set 2, the voltage was set to the 2 volts and the current was set to the 25 amperes. And in the set 3, the voltage was voltage of 2 volt and the current of 40 amperes were used. The observation indicates that during the water cooled process, the advanced process that we are talking about, there was a significant decrease in the welding current from the primary power source where the preheating of the wire begins. In the set 2, the current in the main power source diminished to the 157 amperes, and the set 3, the current from the main power source decreased to the 143 amperes. It is very important to mention that the preheat current in the measure test was consistently set as a 25 ampere. So we can easily see that the total electric power consumed by our process in our third set is minimum. So this was the metal 3D printed part that we have developed, that we have generated through our advanced process. Thank you. If any concern or if any queries there, I am ready to answer it.
So as we can see, there is no